There's an infinite variety of technologies and products and people in the world. And this means that it's impossible to represent every design detail in a method. For this reason, I've worked to distill design for repair down into a threefold strategy which represents the essential characteristics that every repairable product should have. First, the design should resist breakage for as long as possible, so that a repair isn't necessary. Not everyone likes repairing things. I do, and yet, if I have to repair something too soon, or for a second time because of a design weakness, it frustrates me. I value the product less, and that's a really bad thing. Second, the design should enable repair, so that the owner can fix it with their own hands in their own home. They shouldn't have to spend too much time or too much money or rely on the services of an expensive expert. It should be feasible and affordable for an ordinary person, even if they're busy. Third, the design should create motivation for the repair. If the owner thinks, nah, I don't like this product very much, it isn't any fun, doesn't save me time, isn't very useful, well, it's unloved. And an unloved product is much more likely to get thrown away. Now, this is quite abstract and sterile. It's not really enough. It can be regarded as an intermediate step. What I want to do is to create a method that's useful and fruitful for the product designer. Something that gives them a philosophy for their thinking and a framework for their technical decisions. So I'll now be adding some detail to this strategy, but I'll be striving to keep it as broadly applicable as possible. I'm now going to give a slideshow of my own experiences and inspirations, along with some detailed examples of design. This will explain the background and give you an idea how I've come to develop the robust method. This first picture shows me at Massachusetts Institute of Technology in the early 2000s, when I was working at the Field and Space Robotics Laboratory. This was the research group of Professor Stephen Dabowski, and it was a very wide mix of people, a very free-thinking team. What I'm doing here is milling the supports for the bearings of a polymer stretching device. The polymer stretching was to be one step in the assembly of prototype electrostatic actuators, which had potential applications on satellites. The principle was that both sides of a sheet of flexible rubber were coated with conductive paint, making two electrodes. And when you applied a high voltage between these electrodes, the electrostatic attraction or repulsion would either squeeze or stretch the rubber, making the sheet thinner or thicker. And through the Poisson effect, the long piece of rubber would then be caused to extend or contract like a muscle. In the machine shop, they had two great technical instructors, Jerry and Mark. Jerry was a motorcycle fan. He had a Honda, and he was often making custom parts for his motorcycle. And I think Mark might have been into powerboating. And these two, they taught me a great deal about real-life engineering. In particular, they showed me how to recognize what you can build and what you can't. When you're designing a product for easy repair, the first point I noted on the blackboard is that it should resist breakage as far as possible. This is a close-up picture of a heavy-duty stapler by Ernst Nagel of Germany. It's the kind of stapler you might use for binding together thick bundles of lecture notes, and it's an excellent example of something dependable. The mechanism is built out of cast iron and steel, and it's mounted on a wooden base. If you look closely, you can see that the hammer, which drives the staple through the pages, travels downwards in a straight line. In engineering, linear motion like this is often more difficult, more troublesome than rotary motion. Rotary motion has the advantage that the friction usually occurs close to the pivot. This means that there's a moment, a lever effect, which amplifies the force. This helps the mechanism to overcome the friction and keep moving. With linear motion, you don't have this force amplification. And what's more, there are often alignment issues which serve to create extra friction. So here, the designer of the stapler has added two rollers. These take the straight line rubbing motion and convert it into a rolling action, greatly reducing the friction and practically eliminating the chance of this mechanism seizing. When it comes to reliability, this is a great feature. Another thing I love about this stapler is the hammer tone paint. This is very good at hiding the scratches and chips, so the product keeps on looking good for a very long time. In the simplest terms, a moment is a force that's offset, so it twists part of a machine. And the levering effect means that the induced forces can be far greater than the applied force. Now, if you want that part of the machine to move, as we did with the stapler in the previous picture, that's an advantage. But if you don't, it's a disadvantage, because these high internal forces need to be resisted, and they can cause a lot of wear in a mechanism. A caster like the one in the picture has a horizontal axle through the wheels, which is offset from a vertical pivot. This offset makes the caster self-steering, so it follows the motion of the trolley, but it also creates a destructive moment which acts on the vertical pivot. And this is why casters are often high mortality components. They're always wearing out. They're always breaking. This design from Oskar Krieger of Dresden in Germany incorporates some very smart thinking. It has an extra roller directly above the axle, which bears against a round plate on the bottom of the trolley. This roller carries the entire weight which is placed on the caster and completely eliminates the moment acting on that vertical pivot. This makes the caster far tougher and more wear resistant. This example is actually quite old. It dates from the beginning of the 20th century. But I have a few examples of this age because they can show us what stands the test of time. So one way of extending the lifetime of a mechanism is to reduce the forces which squeeze the parts together. But another approach is to add some oil. This produces a film on the rubbing surfaces, keeping them separated and reducing the wear. The thing about oil, though, is that it has to be contained and distributed around the machine. It's messy and it wants to escape. So you can easily end up needing an oil pump and pipes and seals, which considerably raise the complexity and cost of the machine. This picture shows the gearbox of a wind pump on a farm in South Africa. The two large gears are turned by the sails of the windmill, and they drive a pair of connecting rods which lift and lower a long vertical rod. This rod, in turn, operates a reciprocating pump near the ground, which lifts the water. You can see a pair of rings hanging from the pivot at the top of the connecting rods. Every time the pump goes through a cycle, these rings touch the gears. The gears dip down into a sump at the bottom of the case, which is filled with oil. So every time they touch the rings, a little oil is transferred, and the rings also rotate slightly. This means that the oil gradually finds its way up to the pin at the top. It's a very simple way of lifting the oil. It doesn't splash it around, so you don't need any fancy seals, and neither do you require a high-precision oil pump. Here's an electrical example. When a circuit goes wrong, it's usually because the current flows where it shouldn't, or because it can't flow where it should. Switches are common points of failure. What often happens is that non-conductive oxides accumulate on the contacts of the switch, raising the resistance. This can cause the switch to overheat, or even to stop conducting entirely. This switch, designed by Tucker, which is used to control a heater, has a contact link with two flat blades. You can see it at the top of the picture. When the lever is moved, this link snaps down into two matching contact slots. This motion creates a positive scraping action, which wears away any accumulated oxides and ensures a good contact. It's supported by the way that the contact slots are sprung to give contact pressure. What's more, the contacts are redundant. Each blade can touch the slot on both sides, but it only needs to make contact on one side for the switch to work. Lastly, the switch uses a sprung toggle action. This means that when it breaks the circuit, the contacts separate very quickly, so there's only a minimal time for an arc to burn the contacts and generate fresh oxides. Overall, it's an excellent switch design. It's much better than you'll find in most small appliances. This is an optical mouse with the top cover removed. It's used to move the cursor on the screen of a computer, and it's the successor to the traditional ball mouse. The problem with a rolling ball is that it picks up contaminants from the table, dust, fluff, spilt drinks, and over time these combine to form gums which seizes the mechanism. You then have to take out the ball and clean your mouse. In comparison, the optical mouse uses a sensor, essentially a camera, which takes a rapid series of close-up pictures of the texture of the table. And by comparing these pictures using its own microprocessor, the mouse is able to work out in which direction it's been moved. This is symbolic of a widespread trend towards solid-state devices. These use semiconductor electronics and only have a minimum of mechanical switches and moving parts which can wear and need attention. And it's not just a trend among smaller products. There's a good example in locomotive design. In the 1950s, the French National Railways, SNCF, built a series of experimental freight locomotives, the CC-14000 locomotives. These took single-phase alternating current at a fixed frequency and converted it into three-phase alternating current with a variable frequency in order to control the speed and torque of the traction motors. And the two electromechanical converters which did this, put together, weighed 27 tons, and this weight had to ride along in the locomotive. Today, you can do the same thing with a power electronic converter in the locomotive, and it weighs less than a tenth as much. So solid-state devices can make things smaller and cheaper and more dependable, and they can also have more nuanced behavior. But the repairer can no longer see or hear what's wrong, and they also have quite astounding conceptual complexity. There was a figure a few years back that the iPhone had a team of 800 engineers designing its camera alone. So in design for repair, the use of solid-state devices needs to be given careful consideration. You should be looking for new ways to promote repair and to ensure repairability, even in the long term. Over the decades, many machines have become more portable and less understandable. This is an arc welding generator from the immediate post-war era. It's branded Asea, but it was quite possibly built by J.H. Holmes and Company of Great Britain. It follows their design from the interwar period. It's a good example of a machine that was built before miniaturization and before the advent of solid-state circuitry. Essentially, it consists of a three-phase induction motor driving a direct current generator with a drooping characteristic. This regulates the welding arc and means that the generator can be short-circuited without harm. It's a big machine with a lot of thermal mass, and this makes it very tolerant of overload and harsh conditions. It's 75 years old, and it's still going strong. What's more, you can diagnose faults with your own eyes and ears. If you want to check on the carbon brushes, the doors of the generator swing open like the wing cases of a beetle, and you can immediately see how far the brushes have worn down. If you hear a chattering when the machine starts up, you need to check on the contactor, which switches the motor from a star configuration to a delta configuration, and perhaps clean and adjust the individual contacts. And if you want to look at the rotor or the windings, you can even lower a mirror on a stick down through the control box. It's also a machine that's very much built by hand. The generator coils are wound out of copper wire, which is insulated with a helix of fiber tape. And when this machine was built, there were companies that would repair a defective generator coil by stripping the coil, pulling off the damaged insulation, annealing the copper wire, and then recreating this helix of fiber tape. They then take the same wire and use it to rewind the coil. The problem I had with this machine was that it was generating the wrong way round. The plus and minus were reversed. And I thought this probably comes down to the residual magnetic field in the iron of the generator. So I took a truck battery and hooked it up to produce an initial current through the generator before I switched the motor on, thinking that the generator should then amplify this current and reverse the polarity. Unfortunately, it didn't work this time, but with some experimentation, I was eventually able to get it fixed. When a product does break, the second thing I mentioned earlier is that a good design needs to enable repair. This means that it should not only be possible to fix the product, but it should also be practical. Repair is closely related to reuse. At its most creative, reuse involves salvaging valuable and versatile materials from unwanted products and rebuilding them into something completely new. Here I am, together with Chepo, a very charming and talkative woodworker, by the side of the road in Gaborone, Botswana. Botswana is a landlocked country. It doesn't have any ports. This means that many of the foods and materials and products are brought north across the border from South Africa. And when the trucks head back, usually empty, they often have wooden pallets to spare. To make a bit of extra cash, the drivers then sell off these pallets cheaply to Chipo before making their journeys home. Chipo has a couple of helpers, a generator and some electric power tools, and he strips down these pallets for wood and builds articles for the local community. He makes wooden framed sofas with removable cushions, picnic tables, fencing panels like you can see here, and what we're holding in the picture is a large wooden tray that you can use to organize magazines or for muesli and rusks on your breakfast table. This is made out of wood from Dairy Crest pallets. The finish is created by lightly burning spots onto the wood with a blow lamp, and then sealing the surface with colored varnish. The effect resembles the fur of a leopard. The whole idea behind this business is one of freedom. It operates on a patch of sandy wasteland. The furniture stays there at night, and for the most part, nobody steals it. And Chepo is able to build furniture which is well suited to the local people and their lifestyles. It's a case of, if you can build it yourself, you can repair it yourself. Some materials are more open to repair than others. If you think of a plastic bucket, it's very difficult to fix a crack and keep the bucket watertight. In contrast, what we have in this picture is an ugly but successful repair to a tool. A repair that's kept the tool useful for decades. This is a close-up of a slide hammer bead breaker for removing truck tires, made by Mummy Tools of Australia. And this bead breaker has seen a hard life. It consists of a long chisel inside a weighted sleeve, and the sleeve can slide up and down over the chisel. So you put the tip of the chisel on the bead of the tire and pound the sleeve up and down, applying focused blows and breaking the tire free from the rim. Where the end of the sleeve is closed off, where it impacts the chisel, is the point of maximum stress, and it's where the fatigue cracks grow. And every time a new crack has appeared, the owner has repaired it using ordinary arc welding, time and time again. Given the amount of weld metal on here, I suspect that they've carried on welding to add some extra weight. But when they were finished with the repairs, they've given it a fresh coat of the blue paint. So what we have here in the steel of the sleeve is a material that's very open to repair, very forgiving. It can be repaired successfully. And in the blue paint, we have a surface coating which can be renewed. These 2 points are very important in designing for easy repair. Here, we have a pair of crampons. The idea is, you strap these spikes onto your boots, and they give you extra grip when you go hiking over ice and snow. These date from the first decades of the 20th century, from a time before packaged adventures. So you'd put them on, head out into the wilderness, rely on your own skills, and seek out what interested you. The problem with packaging things too much is that it makes people reliant on services. And when it comes to repair, it makes their thinking black or white. People no longer think this is harder to fix or this is easier to fix. They think this is broken or it's not broken, and they no longer look for their own novel solutions. This takes me back to when I went camping as a boy. I was supposed to be learning to tie knots, but I wasn't much good at knots. I was more interested in figuring out how things worked. So I took a long length of rope, and I thought, if I wrap this many times around the branch of a tree, but I don't tie a knot in the end, will the friction carry my weight? Can I use it to build a swing? Now my swing worked, and I learned a lot in the process. Coming back to the crampons, we can see that these were special possessions and they were connected with special experiences. When they've developed cracks in the middle, the cracks have been welded up, perhaps at the owner's place of work or maybe by a blacksmith, and at some point they've had new straps fitted. These repairs have been made possible by the simple shapes used in the design, by the uniform steel plate of the frames, and by the flat hemp straps. Using simple shapes like these is very important when designing for easy repair. They make it so much easier to fix something. Now, simple geometries can sometimes pull in the opposite direction from optimizing parts for strength or for weight, but it's usually possible to find a happy compromise. This is an oil-filled radiator made by Günther of Mardermühlen in Germany. It follows the style of a traditional cast iron radiator, but it's built out of a series of pressed steel plates, each with a disc shape. These are assembled in pairs and seam welded together in a row, making a tank with a large surface area and improving the heat transfer. But the neat thing about this design is that for the heating element, it uses an ordinary immersion heater of the kind that you put into a hot water tank, and this has a British standard pipe thread. So if the element or the thermostat fails, and these are the parts that are most likely to break, you can just find yourself a new immersion heater and a big spanner, stand the radiator on end, and in a matter of a few minutes, you can swap all of the electrical parts. The oil inside the radiator doesn't get wasted, and it doesn't get released into the environment as pollution. Here you can see that the replacement immersion heater I've installed was made in Poland. So this example shows the benefit of widely standardized parts. I'm now going to show you two examples of what not to do. This is a portable water pump. It came from a laboratory, but it could equally be used in plumbing or construction. It's a beautiful yellow color, but more importantly, it's built tough. It has a lot of replaceable parts, and the electric motor runs in a tank of oil to keep it dry. But now and then, you need to open the pump chamber, maybe to clean out silt or to replace the impeller if it gets damaged. And for me, this was an exercise in frustration. It took me about half an hour to work out how to remove the end cover without doing any damage. The cover is secured by a pair of pressed metal wings, each with a channel-shaped cross-section. To lower the wings, you have to take a pin punch and push it through 4 holes to release the white plastic latches you can see in the picture. A snap-together design like this is quite common in electronics, but it's quite uncommon in industrial equipment like this. And I was left asking myself, why didn't the manufacturer cast instructions into the end cover saying how to open it? Or better still, why didn't they secure the cover with a pair of ordinary toggle clamps like you find on the bonnet of a concrete mixer, which everyone knows how to operate? Because at the end of the day, if you're designing a product to be maintained and to be repaired, you've got to let people get inside. This is an alkaline D cell, which I extracted with great difficulty from a torch belonging to my father. It's a police-style torch, all metal in the shape of a truncheon, and the cells are a close fit in the aluminium barrel. What happened here is that one of the cells leaked, and the leakage caused the aluminium to corrode. The corrosion expanded and it seized the cell in the barrel. To get it out, I had to attach a wire by drilling a hole in the end of the cell and driving in a wood screw. And even this didn't get it free until I heated the aluminium to expand it. I nearly gave up, and I think many people would have thrown the torch away. Now, the lesson here is that when you use batteries, even if they're good batteries, you have to reckon on them leaking and design for it. In this case, it would have been good to make the barrel slightly larger and to line it with soft rubber or foam, partly to protect the aluminium from corrosion, but also to give some flexibility so the cells can't get stuck. As an alternative, you could design the battery compartment in two halves, which split open along their length like a clamshell. This way, the cells can never get trapped. Lastly, it's important to think about the electrical contacts and to make sure that they're resistant to the highly corrosive nature of the leakage. One big problem in the modern world is that people are kept apart from the origins and fates of the products they use. They buy something like pulling a rabbit from a hat and discard it like tossing a coin into a wishing well. They don't see the giant mines needed to deliver the rare earth metals for making electronics, and they don't appreciate what happens to the things they throw away. Their throwaways might end up at an energy-intensive recycling center where they get shredded into pieces and imperfectly sorted into their constituent materials. Or they might go along with the rotting food and the plastic bottles and the broken bricks and the old tires and get dumped in a field where people let their animals forage, their dogs and their pigs and their chickens, and where the people themselves dig through their end-of-life products looking for valuable materials to sell. It's a more unsightly and hazardous scenario, but it's admittedly less energy intensive. Depending on where a person lives in the world, they may produce from a few kilograms to a few tens of kilograms of electrical and electronic waste every year. And this is quite apart from the broken furniture and the junk cars and the demolished buildings. If you add that up across the whole world, it's about 1 million tons a week. That's a crazy amount of waste and pollution. It's important to recognize that design for repair goes together perfectly with design for recycling. They have the same priorities. So you can design a product that's tough and repairable and which has a long life, and then at the end of its lifetime, it's also easy to recycle. Both require that the product is simple to take apart, that it uses larger components and fewer materials, and that these materials are also easy to identify and rework, like metals and woods. Now, much of this remains hidden in everyday life, so I'm now going to take you to see a dump. This is the dump in Ladybrand, which is a small country town in South Africa. Here there's a little tracked loader. It looks like it must belong to the municipality, but looks like it's missing its tracks. Yep, this is the dump. So this looks like it's the recycling area where they gather plastic and put it in bags.
How you doing, my friend?
Good and you say. I'm the way I live to go in
To go to Ladybrand?
Yes.
You want to ride?
Yes, sir.
Yeah, hop on.
Hop out.
Hop on. I might not be going all the way, but hop on. You know, like the entrance by the dump?
Yeah.
I can like drop you there if I don't go into the center.
No problem.
All right.
Yes, sir.
What's your name?
Okay.
Michael. Chris.
Yes, sir.
Hop on. Where do you want to go?
I want to go to the scrapyard.
To the where?
To the scrapyard.
The scrapyard, the Eddie's place.
Yes, sir. I say,
Eddie's place.
yes, sir.
All right.
I'm a bad.
All right, get on.
Can you move on? That's all.
All right. Yeah, no problem. Is this the right place for you guys? Pleasure. You too.
Thank you very much.
Looking beyond the technical details, the last essential part of the puzzle is whether or not the owner of the product wants to repair it. It needs to create motivation in order for it to get fixed. This is a highly emotional thing, and it's difficult to define or to measure in any useful way. But at this point, it's helpful to take a look at some of the changes that have occurred in society, at the complexities that have arisen as products have become more sophisticated. There's what I call the paradox of enlightenment versus entanglement. Today, the designer has a deeper understanding, better modeling, stronger materials, and faster communication. These things all help to deliver a dependable product. And yet, there are fresh obstacles. There are more border controls, longer supply chains, stricter regulations, and, for better or for worse, the rising complexity of the products themselves. These all work to blur the relationship between cause and effect, to obscure what's sensible and responsible. And when it comes to changing anything, they work like treacle. So, amidst these progressions and regressions, it can be very challenging to find the right balance. In the picture, we have Pennsylvania Railroad GG1 electric locomotive number 4876, hauling a passenger train through Kearny, New Jersey in March of 1980. 4876 is a very interesting example because when the locomotive was 14 years old, in 1953, it was involved in a serious crash. It was pulling a train into Union Station in Washington, D.C., when the train brakes failed, and the locomotive crashed into the station building, fell through the floor, and landed in the basement. The timing of the accident was highly inconvenient because it came 5 days before the inauguration of President Dwight Eisenhower. So the railroad built a temporary floor over the crashed locomotive to hide it, and only came to recover it from the basement after the inauguration. Now, it's one of the biggest locomotives ever built, and they found that they couldn't pull it out of the basement in one piece. So they had to cut it into sections. They took the sections back to their yard and laid them out for inspection. And they came to the conclusion that it was only the superstructure and the bogie frames that were destroyed. The rest of the parts were still in good order. So they ordered replacements for the damaged parts, had these specially manufactured, and rebuilt 4876 so that it was good as new. The locomotive then went back into service and stayed operational for 30 years after the accident. It's a very inspiring story of the determination to repair something. This man sells grilled corn on the cobs to travelers delayed at Maseru Bridge. Maseru Bridge is one of the major border posts between South Africa and Lesotho. I'm showing this picture because governments often obsess over money and numbers and statistics, and they lose sight of the people on the ground, of their well-being and satisfaction. This man has to assemble and repair all of his own equipment. He has to be independent. It's the only sensible option. Now, individuals don't care about abstract measures of success, like gross domestic product or net migration. They care about what they can actually do. My work in Design for Repair has the same focus. It's not about ticking boxes or reaching quotas. It's about giving people more autonomy, about helping individuals to do more things for themselves. I must also say that his grilled corn tastes particularly good. It has an earthy cereal flavor, very strong and authentic. And when he grills it just right over the charcoal, it stays juicy and it somehow acquires a hint of toasted caramel. When a country becomes more wealthy and more industrialized, its citizens acquire more possessions. They own more things, and sometimes they don't know what to do with them. It's difficult to count exactly how many things a person owns. It's like trying to count the parts of a machine. You might have a printed circuit board that's populated with electronic components, and you could count it as one part or as 10. In the same way, you might walk into a person's garage and see a box of tools, and you could count it as one possession or as 10. But what you can say for sure is that in Western countries, a typical family now has thousands, if not tens of thousands, of possessions. This picture shows a row of self-storage units being built on the outskirts of Bloemfontein in South Africa in 2023. In the last few years, 3 different companies have built self-storage facilities along this road, and there are now hundreds of storage units to rent there. Now, South Africa is a fairly average country by global standards, and Bloemfontein is a fairly average city by South African standards. But here you can see that on this average level, people are already finding that they have too many things to keep at home. In the United States, the picture is even more extreme. There's a recent figure that there are now over 7 square feet of self-storage for every citizen. This means that theoretically, every man, woman, and child in the country could stand inside self-storage at the same time. Sometimes a product gets stored because it has a minor fault which can't be repaired, but the owner doesn't want to waste it. Other times, it ends up in storage despite the fact that it's in good working order, because it's no longer useful or desirable. But most things end up there because products have simply got so much cheaper over the decades. When designing cheap products, it's important to recognize that there are 2 possible philosophies. There's the philosophy, I want to help you, and the philosophy, I want to cheat you. And in design for repair, it's essential to follow the former rather than the latter. You need to be building things that are going to be used and loved and valued in the long run, by design. This is a smartphone repair store at the Central Market, again in Gaborone, Botswana. I visited Gaborone in the spring, in October, when the trees blossom, and if you walk under the purple jacarandas and the yellow silky oaks, you'll see lots of colourful hand-painted signs advertising different repair services. You can find someone who will come and fix your refrigerator, or your sofa, or your car seats, and much of the repair work takes place in the open air, under the sun, which means that repair is very prominent in Gaborone. It goes to show that despite the rising complexity and falling cost of many products, there's still a lot of enthusiasm for fixing things. Partly it's a matter of financial necessity, and partly it's a lifestyle choice. People want to save money, but they also want to maintain their independence. Now, modern products don't always make it easy. If you look at refrigerators, the compressor is usually welded shut inside its housing. So before you can free up the motor or replace the reed valves, you've got to saw it open. And when you're finished, you've got to weld the housing shut again. You'll never see that practiced in Europe, but it does happen elsewhere, particularly in Asia. When it comes to smartphones like these, the screen is essentially a glued glass sandwich, so if it gets cracked, there's nothing you can do to fix it, which means that the supply of the right spare parts is critical. And these men, when they replace a screen on a smartphone or a tablet, they keep the broken one and they lay it out on this table at the market to advertise their trade. I've always been a night owl. When I was in the academic world, I'd often stop for late-night conversations with the security guard. His name was Atta. He came from Persia, and we shared an interest in lamps. Now and then, someone at the university would throw away an interesting lamp with a minor fault. So we'd do repairs, we'd swap lamps, and we'd talk. This is an LED lamp that Atta found. It was discarded because one of the 3 glass shades was broken. So Atta took a sheet of office paper, rolled it into a tube, taped it together, and made a new lampshade. This goes to show that a repair doesn't need to be perfect. It just needs to get the job done. And if the repair is a bit improvised, it adds some character. What's more, the satisfaction in doing things for yourself, in taking a problem into your own hands and relying on your ingenuity, it gives a stronger sense of ownership. Looking at the big picture, when individuals carry out repairs, it helps them to escape from a pure dependence on money and from the idea that everything is a commodity. Over the years, I've talked to hundreds of different people, not just about the technicalities of repair, but also about their lifestyles and their priorities. There was the Namibian cattle farmer who welded an extra layer of metal onto a worn axe to extend its life, because otherwise he'd have had to drive 250 kilometers to buy a replacement. There were the night workers of Berlin who ground the tram tracks flat in a shower of sparks to smooth out the bumps and improve the ride for the passengers. When I was working as a journalist, there were also the more famous characters who counseled me about the challenges of innovation and about fighting the status quo. Richard Noble, the man behind the supersonic car, said to me, I quote, "There's a great time and great fun to be had out there. If only people would be prepared to change their organizations, to think, and to trust people." I also visited the late Trevor Bayliss, inventor of the clockwork radio, at his home on an island in the River Thames. And Trevor said to me, Chris, you don't want to be the richest man in the graveyard. There ain't no pockets in a shroud. Over time, I've noted down everything I've learned. I took a large sheet of paper and I wrote down the important points, the unimportant points, and everything in between. And then I began to eliminate what was irrelevant and to remedy the omissions, all the time comparing what I had against various examples. And I worked to identify the overlaps and the links. It became like a Venn diagram, and there were several iterations of this sheet, several colorful networks of ideas. And in the end, I was able to distill it down into a broadly applicable method, represented by the memorable acronym ROBUST, which summarizes everything you need in design for repair. It's now time for me to unveil the components of the method. Here on the blackboard, I've drawn a colorful matrix. And reading down the left-hand column, you can see the memorable acronym, while along the rows, we have the 6 components. So, a product which is designed for repair using the robust method should be rugged, open, balanced, useful, satisfying, and transformative. Next, I'm going to explain the individual components in detail, along with 6 corresponding examples of good design.